Feathers are one of nature's most amazing creations. Every day they glide around us, effortlessly carrying birds on the wind. Yet the origin of feathers has always been a mystery. An evolutionary puzzle that has driven scientific passions for more than a century. How did these marvels of natural engineering evolve? The answer lies hidden in their dazzling design and in fossils from the ancient past. In the last few years, new fossils have been unearthed, shedding light on the feathers' elusive origins. Fossil dinosaurs covered with feathers. Could dinosaurs have been the first to be covered with this incredible innovation? How did they use them? Is it possible that dinosaurs could fly? To answer these questions, scientists from many fields are working together, employing the latest research techniques to unlock the feather's surprising history. Suddenly, the mysterious origin of the feather is now coming into focus, and the astonishing answer will change your definition of feathers, birds, and dinosaurs. Rick Prum's lifelong fascination with birds eventually became focused on the one feature that set them apart from all other animals, their feathers. His obsession with their hidden history resulted in an entirely new theory of feather evolution.
A lot of the most amazing things about birds are consequences of the fact that they have feathers. So they have beautiful plumages that we use to recognize birds. They have a coat of feathers that allows them to stay warm on cold days like today. And obviously they use their feathers to fly. And these are all aspects of avian biology that make birds particularly fascinating.
In the last 20 years, biologists have shown that birds are the only living descendants of a long line of fierce predatory dinosaurs. Yet this impressive genealogy has failed to explain when, why, or where feathers first appeared. Like a detective on a cold case, Rick hoped a fresh look at the evidence would reveal something new.
I was dissatisfied with the classic theory of how feathers evolved, and I realized that some of the critical elements to a new story, a new hypothesis for how feathers evolve, could come from how feathers grow. Hidden within the details of how feathers grow were clues as to how feathers evolved, clues that would unlock their evolutionary history.
While Rick searched for clues in the lab, half a world away in Liaoning, China, paleontologists were searching for clues written in stone. The fossils they found revolutionized the field. Here were dinosaurs with feathers, or something like feathers, covering their skin. Liaoning allowed scientists to peer through a window into the past to a time 128 million years ago when dinosaurs ruled the earth. To discover how and why feathers evolved, Rick sought out scientists whose passion to answer the question matched his own.
And just like humans are primates, birds to me have always been dinosaurs.
And we're having to rethink everything about birds.
And it's a very different thing when you realize that dinosaurs are not extinct, that there's in fact 10,000 living species of dinosaurs today, which are birds, but they're also dinosaurs.
Feathers present an extraordinary evolutionary puzzle. Following the clues left by feathered dinosaurs is made more difficult by the astounding diversity of feather form and function. Feathers come in many shapes, sizes, and colors that perform an array of duties. They are lightweight yet strong, flexible yet resilient. From tufts of down that provide warmth to sleek flight feathers that create the streamlined wing. An amazing palette of colors and patterns help birds hide from predators or advertise for mates. It is hard to imagine all the things that feathers can do until you see them in action. Rick gets up close and personal with a rough-legged hawk, or should we say, a rough-legged dinosaur.
I got some arteries down there. The body of the bird is covered with contour feathers. The contour feathers form the outside, the outline of the bird, and are the primary protection from rain and from elements, and also create a lot of the plumage patches that allow us to identify the bird as a rough-legged hawk. The bottom parts, the base of many of the contour feathers, are downy to provide additional insulation. Now, on the wings and tail, we have flight feathers. And these flight feathers are asymmetrical in shape. The leading edge is narrower than the trailing edge. These flight feathers provide the aerodynamic forces that allow the birds to fly.
It is the delicate airfoil design of the flight feathers and the aerodynamic forces they create which allow lift and keeps birds airborne. A deceptively simple and elegant design with spectacular results. The amazing diversity of the feather is built on a simple idea. Feathers are branch structures like trees. The way their branches are shaped and work together is a marvel of microscopic engineering, as delicate as it is effective.
So feathers are branch structures. The main shaft going up the center of the feather is called the rachis. Connected to the rachis are numerous smaller branches called barbs, and connected to the barbs are even smaller, nearly microscopic branches called barbules. Together, these small filaments interact to create the flat, planar surface of the feather, which is called the vane. A feather that has a complete vane is often called pennaceous. The flat, planar vane of a pennaceous feather is formed by the zippering interaction of the barbules from adjacent barbs. The barbules in the pennaceous feather function a lot like Velcro. Interlocking together, they create a surface that is strong and resilient and that can withstand the forces of flight.
Although the microscopic design of feathers provides many advantages to the lives of birds, this hidden complexity makes it even harder to explain how feathers evolved. The answer to the mystery of feather origins lies in fossils from the ancient past and locked within the feather itself. The first clue in the mystery of feather evolution came from the 150 million-year-old rock formations in Solnhofen, Germany. The thin, fine-grained limestone sheets open like the pages of a book written by nature long, long ago. One day in 1861, a page was turned that would unveil the most famous fossil in the world and a wonder of its age. Luis Chiappe, an expert on ancient birds, deciphers these pages of stone.
Well, Archaeopteryx was found in the middle of the 19th century, soon after Charles Darwin published his book on the origin of species. It was found in the midst of a huge controversy, the evolutionary debate, and it played such a critical role in turning this evolutionary debate to our understanding of how animals have transformed over time. It became an icon of evolution, some kind of paleontological Mona Lisa. So definitely the role of Archaeopteryx 150 years ago was that role of missing link, that role of intermediate between, on the one hand, animals that looked dinosaurian and animals that were birds, modern birds. What was critical at the time is that we have an animal with claws, an animal with teeth, an animal that looks very reptilian, but yet it has modern feathers.
Archaeopteryx was the first bird, but its feathers were already identical in shape and structure to those of living birds, so it tells us nothing about where feathers came from. That answer must be hidden in the ancestors of birds, fierce, meat-eating dinosaurs called theropods. You can look at the history of dinosaurs like a family tree. The first branch are the ornithischians, vegetarians like Triceratops and Stegosaurus. On the following branch are the sauropods, the giant long-necked dinosaurs like Apatosaurus, also known as Brachiosaurus. The closest relatives of these giants were the bipedal carnivores called the theropods, including Tyrannosaurus rex, Velociraptor, and birds. In the 1960s, John Ostrom of Yale University discovered another member of this nasty club, the raptor dinosaur Deinonychus. It played a critical role in proving the connection between birds and their theropod ancestors. Dinosaur biologist Jacques Gautier identifies the similarities between birds and this frightening theropod and demonstrates how its savage hunting habits may have laid the groundwork for flight.
Deinonychus changed us over from the conception of dinosaurs you see in the mural where dinosaurs are overgrown lizards to that these were active, cursorial, ran around for a living, very much more bird-like creatures, and that all stemmed from the description of Deinonychus anterophus. Well, you can just start with the head. Another obvious feature is rather than the teeth going underneath the orbit, it's just primitively the case in theropod dinosaurs. The entire tooth row is in front of the eyes. We're eventually going to make this into a beak. And you look at the forelimbs, you see these much longer arms. Dinosaurs start out with their forearms are only about half the length of their hind legs. Think of the Tyrannosaur up there with really diminutive little hands. As you get into these raptors within the theropods, they start getting these really long arms, as you can see here, that are nearly as long as the legs, with these gigantic mitt-like hands, a three-fingered hand that's fully a third the length of the entire arm. The old reconstructions, as you see here, showing kind of the limp bunny, wrist attitude. We've come to appreciate in recent years when we've gotten completely articulated hands, just like birds. All the motion takes place here in the wrist. They flick the hand fore and aft. And what this animal is doing is really playing praying mantis, in that it's holding its arms up folded against its body. The prey item doesn't think it's as close as it is, so to speak. So they have a stereotype motion where they go down and forward, grab their prey, up and back, down and forward, up and back. That's the flight stroke. That's exactly the way birds fly today. And we always wondered, well, how do you get power on the upstroke? They actually make this transformation in a muscle called the supracoracoideus that shoots the arm forward. And in birds, it actually lifts the arm up. But the motion made here is exactly the flight stroke. So these guys are grabbing prey items a considerable distance from their body. The prey item struggles in their grasp, and as a consequence, they stabilize the shoulder joint by fusing the two clavicles together to make a wishbone. And then they had to pull the prey back to them. There's power on the upstroke before you're flying. And so virtually all details of the flight stroke originate before flight. And that's the best part about the fossil record. There's no way you'd look at a flying bird today and go, obviously that forelimb came from a raptorial organ used to seize and secure prey. No way you would guess that. That's only the information you can get from the fossil record. These beasts were, ruling the day, and for 180 million years, dinosaurs were out in the daytime, and all the mammals are out at night. And the largest Mesozoic mammals are, maybe the size of a possum or something. Most of them are mouse-sized. So we came out at night and stayed tiny for 180 million years. After the asteroid hit, knocked out at least the big dinosaurs, if not the little ones, the birds, but knocked out the big dinosaurs. That's the only time that mammals had the gumption to climb down out of trees and come out in the daytime. So we're lucky. We would not be here.
How did the arm motion of theropod dinosaurs evolve into the flight stroke of modern birds? To answer that question, Steve Gatesy is exploring just how birds use their bones, muscles, and feathers to fly.
What we're seeing here is a pigeon flying in a wind tunnel. This is the wind tunnel that Ken Dial from the University of Montana made, and he brought it to Harvard so that we could do a collaboration with Ferris Jenkins. And what we've done is taken the wind tunnel and put it in the X-ray facility so that we can take not only light video, as you see here, but also X-ray video, as you'll see in a minute. What the wind tunnel does is actually a big fan that creates an airstream through a plexiglass chamber that allows the bird to fly essentially in place. And so, although the bird seems to be stroking along rather slowly here, we've We've shot it with high-speed video, so it's actually flapping 6 times a second and flying at about 13 miles an hour. So what I've been doing is basically reconstructing that wind tunnel situation along with the cameras in this animation program in 3D. And so what we can do is take those videos and frame by frame paste them onto little cards essentially, so that if we're looking from the side, this is the picture we'd get from the side camera. If we're looking from above, here's the picture we'd see from above. And then that X-ray camera is going to stick in right on the side here. And by bringing in frame after frame, we've essentially then recreated from 3 different 2-dimensional views what was happening at any moment during that experiment in the wind tunnel. And so we're able to measure each of these motions. How is it moving up and down and forward and back? How is it pitching and rolling and yawing? And ultimately then how are the wings responsible for producing those movements? And so how do they seem to pull off this amazing variety of things they can do? I think we've certainly gained an appreciation for just how complicated it is. How much they move, although it appears very stable to our eye. They're doing lots of small movements, compensating for a movement they might make during the downstroke, and then they'll undo it during the upstroke. Many of the people interested in flight are studying the outside of the bird, and rightly so. How the wings are moving, how those are producing the aerodynamic forces. Others are working sort of from the inside out. How are the muscles and the nerves creating the motors that are going to move this wing? At the same time, paleontologists are interested in skeletons and finding out how these fossils might have worked and how that relates to the origin of flight. And we'd like to think that the skeleton is really where all those intersect. And so a better knowledge of how the skeleton is moving in these living flying birds, I think will really help all those fields. Not only for understanding how these joints work and how they might have worked in fossils, but for really understanding how the birds sort of pull it off.
Birds are the only animals that use feathers for powered flight. For over a century, the incredible adaptations of flight feathers would lead biologists to believe that feathers originally evolved for flight. But would this theory ever get off the ground? With Archaeopteryx, feathers seem to have burst upon the scene fully formed, and biologists had to create theories about what primitive feathers might have looked like. They turned to the most amazing function of feathers, flight. They surmised that feathers evolved from reptilian scales, scales that grew long and thin, making them useful in flight.
One of the ideas about the origin of feathers was the classic notion that feathers are derived scales, modified scales. And therefore, for the people who envisioned this transition, they had to come up with a scale that was becoming longer and longer and longer in order to match the shape of a feather, and which sides were being frayed in order to also mimic the veined appearance and the appearance of barbs that feathers have.
For over a century, biologists had to create theories about what primitive feathers would have looked like. For most of the 20th century, the most popular theory about the evolution of feathers hypothesized that feathers evolved from elongate scales, and that these elongate scales evolved for some function in flight. Of course, that result was completely overturned with the discovery of Sinosauropteryx.
Sinosauropteryx was a small dinosaur who lived here in what is now Liaoning, China, 120 million years ago. Killed by a cloud of poisonous volcanic gas, its body was one of thousands entombed in the ashfall and preserved in astounding detail in the rock. In 1997, it gave scientists their first glimpse of primitive feathers, and they looked nothing like elongate scales, spelling trouble for this theory. It is an experience paleontologist Phil Curry will never forget.
The specimen was brought on the table in front of me, and it was in one of these beautiful Chinese silk boxes. When the box lid was lifted up and I looked at the specimen for the first time, within a millisecond, my eyes had been drawn to these feather-like structures on the outside of the body. I knew that, hey, this is something real, and this specimen is unbelievably exciting.
Preserved as a black halo around the skeleton is what appears to be a fine, downy covering of primitive feathers. Feathers on a theropod dinosaur. If this dino fuzz was indeed primitive feathers, then their origin would have occurred early in the history of these dinosaurs.
We could see that along the bottom of the tail of one of the specimens were very, very thick stalks. And that coming out of those thick stalks were many, many very fine fibers. And if you had to make an analogy, it would be with down feathers, because that's exactly what they looked like. We also knew from one of the other specimens that there were these feather-like structures that had been broken in cross-section, and when you looked at that, they were hollow, and they looked very much like the stalk on a feather tube. So I think the strongest evidence we have right now is that what we see in Sinosauropteryx is a simple down-like structure, very similar in appearance, in having a central stalk and a very simple branching structure coming off of it.
But these fuzzy structures weren't flight feathers. What could they possibly have been used for?
The feathers, or the feather-like structures on Sinosauropteryx, are there simply as insulation, and they're there to keep a warm-blooded animal warm. In a way, I had always known that we should expect to find feathers on a dinosaur, because there were so many characters that birds and dinosaurs shared that the majority of paleontologists had already accepted the idea that birds were the direct descendants of dinosaurs, and in fact that birds were, in a sense, dinosaurs. And Liaoning provided that answer. We always hope for these things, but whether you expect to see it in your lifetime is another matter, of course, and I hadn't expected to see it in my lifetime. And yet I was one of the very first people to be privileged enough to look at a specimen of one of these feathered dinosaurs, and it was really exciting, I'll tell you.
But if the downy coat on Sinosauropteryx was made of primitive feathers, they certainly bore no resemblance to scales, elongate or not. After 100 years with no evidence to support it, the elongate scale theory had reached the end of the line. So, if feathers didn't come from elongate scales, where did they come from? Hoping to answer that question, Rick decided to look into the growth of feathers, and there he found an oddly shaped key, opening the door to their past.
The most fundamental consequence of how feathers grow is the realization that feathers are totally tubular. Really, most of the details about feather biology, their structure and function, can be understood as consequences of the fact that feathers grow as tubes of skin.
Rick hypothesized that the development of modern feathers mirrored their evolutionary history, and he looked to the growth of an individual feather for clues. Every modern feather begins as a small outgrowth of skin, a feather bud, which elongates into a hollow tube. The inner layer of the tube divides into a series of long ridges. These ridges will become the barbs of the feather, the branches that form its light and flexible body. On one side of the tube, new barb ridges begin to form. These ridges then grow around the tube. On the opposite side, these ridges collide and form the shaft of the feather. As the feather continues to grow, new barb ridges fuse to the shaft. After almost 2 weeks, this tubular shape is transformed into the familiar flat surface of the feather as the barbs expand and begin to unfurl. This tubular growth pattern gave Rick the idea for his theory and explained how the tufted structures on Sinosauropteryx could be feathers. Rick's theory proposed that feathers evolved in stages similar to those each feather passes through as it grows from a simple tube to a complicated vein. Rick realized that each stage is built upon the one preceding it. The sequence of developmental stages could be used to predict the evolutionary stages that led to the modern feather.
The goal of the theory is to try to imagine the most primitive feathers and the series of increasingly complex feathers that evolved into the diversity that we have today. I hypothesized that the sequence of events in feather growth could be used to unlock the evolutionary history of how feathers evolved.
Rick's theory predicted that the first feather would be a simple hollow tube. The next stage was a downy feather tuft formed by dividing the tube into barbs. Then, when barbs began to grow around the tube, the first rachis or shaft evolved. With the origin of barbules came the first doubly branched feather. Later, barbules evolved matching hooks and grooves, which hold the barbs together like Velcro. This was the first feather with a coherent vein, which could be used in flight. Only then could the modern flight feather evolve its airfoil shape by growing asymmetrically.
Or the real innovation in feathers is the origin of that first tubular feather that provided the opportunities for all the subsequent diversity that we see. And that's what really makes feathers unique.
To confirm the theoretical stages in feather evolution, Rick teamed up with biologists Matthew Harris and John Fallon. They put Rick's theory to the test by studying how feathers grow on developing chickens. They eavesdropped on the molecular conversations that genes hold as feathers develop. This field of science is also known as evo-devo.
Evo-devo, or evolution and development, is, to sort of paraphrase, is the study of how development translates genetic and environmental variants into form, different types of structures that you may see. For example, whether you get hair, teeth, gland, or feather.
Rick and Matt discovered that there were two genes that worked together to prompt the growth of feather buds, tubes, and barbs as the feather progressed through its stages. The genes were named sonic hedgehog and BMP2. They used a blue stain to show where these genes were turned on during different stages of development. At first, a blue spot shows where the feather bud is beginning to grow into a tube. A few days later, each spot becomes stripes, showing us where sonic hedgehog and BMP2 have been turned on to create the barbs and rachis. Each successive day, the growing blue stain traces the action of these two genes as they orchestrate the complex growth of a feather. Here was the molecular mechanism by which the evolution of feathers could have occurred.
And so the exciting thing that came out of this research not only was a description of how you make a branched feather, but also that it's the reuse of these rules, almost like gears, that allow you to get these complex forms. Not only are the developmental mechanisms being discovered, but also these are going in place with fossils that are being uncovered at the same time. And so collaborative efforts between developmental biologists and paleontologists and evolutionary biologists are leading to the formation of these types of theories that lead us to understand how you might get a feather.
And so from absolute opposite ends of the scientific spectrum, there's support for the same notion, the same idea that there's a connection between how feathers grow and how they evolved.
The genetic gears they'd discovered provided the mechanism by which the hierarchy of feather evolution could have occurred. If they were right, they'd actually taken a peek into the black box of evolution and seen it at work. But the only way they could know for certain would be to see the stages of feather evolution reflected in the fossil record. Would the incredible fossil beds in Liaoning, China hold the answer? Could Sinosauropteryx, the first fuzzy dinosaur, be covered in simple tubular feathers like those predicted by Rick's theory? Some scientists were not convinced. Fortunately, Liaoning furnished another fantastic fossil with much more than fuzz.
Caudipteryx is a wonderful little animal. It's got these downy-like feathers covering all its body, and on the backs of its arms, it's got fairly short, stiff feathers in the sense of what we would call a modern bird feather. And at the end of the tail is a fan of feathers as well. When you look at the Caudipteryx feathers under a microscope, it's quite clear that you can see the rachis, you can see the barbs, and in some places you can even just make out what you think are barbules. Whether you can make them out or not is irrelevant in a way, though, because when you look at the feather structure itself, it's clearly a flat vein. I mean, these barbs are being held together by something, and it only makes sense that they would be barbules. Towards the base of the feather, you get basically a downy or plumulaceous section of it. That, of course, is the part that doesn't have to hold together in a modern bird feather. In fact, it's tied into insulation more. And it's exactly that way in the Caudipteryx feathers. And if you take measurements of the lengths of the barbs and the approximate size of the barbules and the width of the shaft and everything, they line up absolutely perfectly with any modern bird. So you cannot distinguish them.
Though these were certainly veined feathers, they were not used for flight. They lacked the airfoil shape created by asymmetric growth. What purpose, then, could they have served?
Caudipteryx, I think, shows us a transitional stage where these dinosaurs have now developed another purpose for feathers. Dinosaurs, throughout their history, were animals that were very visual. They were animals that displayed in a lot of different ways. So if they wanted to attract a mate, they would have a big crest or a big frill on their head. And, or if perhaps they wanted to scare off an enemy or a potential enemy, they could do the same kind of thing, develop these crests and frills and ridges and bumps and all kinds of things. And dinosaurs were very, very good at that kind of thing. Well, the trouble is if you do that in bone, it's a very expensive way to do it, and of course you can't change it. But if you've got something that's keratinous, that is keratin on the outside of your body, and it's lightweight, and you can shed it, then suddenly you've got a new way to display. There's a lot of things you can do with feathers that you just can't do with bones, and it's a cheaper way to do it. And I think that probably dinosaurs like Caudipteryx had developed these long feathers on the backs of the arms and at the end of the tail as a way of displaying. Now, that's not the only explanation, and of course it's hypothetical, and unless we go back in time, we may never know exactly what they were doing with those feathers.
Most biologists agree that Caudipteryx was a theropod dinosaur, but others were not so sure. They doubted that Caudipteryx really was a dinosaur. They claimed that it was just a flightless bird.
No one could deny that Caudipteryx had completely modern feathers on the tip of its tail and on its arms. But in 1998, when Caudipteryx was first described, there was a small but vocal group of critics that hypothesized that Caudipteryx was merely a flightless bird, sort of a Cretaceous ostrich. And consequently, they held that the case for the theropod origin of feathers prior to the origin of birds had yet to be demonstrated. For that reason, what was really required was a clear instance of feather-like structures or primitive feathers found in the skin of a theropod dinosaur that was, without a doubt, not a bird.
The dinosaur feather mystery was not yet solved, but Liaoning was about to reveal its next crucial clue: feathers on ferocious meat-eating raptor dinosaurs, much like those made famous in Jurassic Park. In 2001, a rock was split open to reveal mirror images of an extraordinary fuzzy raptor, Sinornithosaurus, affectionately nicknamed Dave. For paleontologist Mark Norell, it was the find of a lifetime.
Well, this specimen, when I first saw it, it just blew our mind. That our Chinese colleagues, Ji Chang, said they had something really special, that we had to get to China to see it. And when I saw this, it is just amazing. You can just see it, everything is just spread out before you. And then it's completely covered with a fluffy or feathery body covering. And later, after a lot of study, the sort of details of this feathery covering sort of revealed themselves to us. But when we first saw it, it's apparent as what it is. It's a fluffy feathered dinosaur. What we're seeing is the evolution of what we would call a feather of modern aspect, almost in action. The most primitive animals like Sinosauropteryx have just single filaments, and you can see some of that on this specimen here, which we call Dave. Mostly appear on the head and other places that you can trace individual filaments all the way down from their tip to where that they would have contacted the skin. And then finally, on the back of the trailing edge of the forelimb, we can see self-organized structures which form a herringbone pattern and really hint at, a feather, a real feather of modern aspect, where you have, a vein that's self-organized into these parallel barbs coming down and meeting the central shaft, and just in the exact place that one would expect to find them on the trailing edge of the forelimb.
Even with all this incredible evidence, there were those who still doubted that these were feathers.
It seems like everything that we've ever found before, whether it was Caudipteryx, that some people said was a flightless bird, wasn't conclusive enough. Then we found Dave. Clearly it was covered with a body covering. We felt that we were able to see feathers of modern aspect in it, but not everybody believed us. So we needed to find something better.
In 2002, they did. Mark Norell and his colleagues discovered another feathered raptor from Liaoning with irrefutable modern feathers, as this enlarged image shows.
This white line right here is the shaft, or the rachis, which goes down the center of the feather and is a tubular structure. And then emanating from that on each side, we have these black filaments, which are the barbs, which together form the vein of a feather. And
so the planar vein in this portion is likely to be held together by barbules,
right,
since we can see that in one particular spot the feather vein has unzipped, just like we see in a modern bird.
Exactly. It's unzipped, and then down here it's zipped back together again. So.
There is no longer any doubt the raptor dinosaurs had feathers just like a modern bird. The case was closed. But these were not flying dinosaurs. Their feathers lacked the asymmetrical design that gives flight feathers their aerodynamic shape.
One thing we can tell is that what they didn't use feathers for, and that's that they didn't use feathers for the origin of flight. You can make some guesses, though. I think one of the best guesses, and something that a number of us have talked about for a long time, is that probably it had something to do with temperature control initially. And then as far as the development of the different kinds of feathers, from ones that cover the body to ones which are used for aerodynamic capabilities and things like that, it's at least conceivable that they were used as display structures, which were then later co-opted for the origin of flight. Usually as paleontologists, we make a lot out of very little. We find one little bone and one little trace of feather and things like that. To find something which is just so beautiful and reads so well and is so convincing and so clear, all in one specimen, really makes this one of the great dinosaur specimens in the world.
These raptors seem to have wrapped it all up. But one final question remained. How did flight evolve? If the feathered dinosaurs from China did not fly, that left Archaeopteryx as the first true bird capable of powered flight. But how did flight develop? Were the first flying dinosaurs fast runners who caught some air while grabbing for prey with feathered arms? Or were they tree climbers that began as gliders only to later turn it into powered flight? Using Archaeopteryx as an example, Luis Chiappe explains the two competing theories of the origin of flight.
Origin of flight has been polarized into opposing views. Some people believe that flight evolved from the ground up, from animals that were running, and by flapping these feathers, these running animals were able to run faster and to leap longer, and eventually, when they became smaller, they became airborne. And on the other hand, there are people who support the idea that the predecessors of birds became tree climbers and started climbing trees and having a more arboreal lifestyle, and jumping from one branch to the other and onto the ground. And by doing this, they slowly perfected the ability to fly.
In 2003, a fossil like no other was found at Liaoning. It may hold the answer to the origin of flight. Meet Microraptor, a small tree-climbing raptor with asymmetrical flight feathers arranged on four wings. One pair for its arms, another for its legs, It's the most important fossil find in bird evolution since Archaeopteryx. Zhu Jing, a paleontologist with the American Museum of Natural History and the Chinese Academy of Sciences, made this exciting discovery.
Microraptor is the most exciting animal I have ever described. At the very beginning, we didn't realize that we have a very important discovery at hand. But when we look at detail, it tells us a totally different story.
It was a story unlike any other read in the fossil record. Was flight pioneered by a dinosaur with wings on all four limbs?
It's identical to the flight feather in flight birds today. Actually, I think the Microraptor is not far from the first birds.
If the aerodynamic feathers on the legs of Microraptor can be confirmed with additional specimens, then Microraptor will certainly go down in history as one of the most important fossils of this century.
Amazingly, it now seems birds may have begun their journey to powered flight by sporting 4 wings, not 2, to help them glide from tree to tree. It would not have taken much for the grab and pull action of hunting raptors to turn that glide into the wing stroke of modern flying birds. In the past, birds have always been recognized as members of a distinct group. 2 things set them apart from other animals: having feathers and their mastery of flight. But with its modern-looking flight feathers and aerodynamic wings, Microraptor has robbed the birds of both these distinctions in one fell swoop. By working together, scientists from diverse fields have been able to trace the sequence of stages feathers progressed through as they evolved. Not only have they peeled back the layers of living tissue to see evolution at work, but they have peeled back the layers of time to see their theory written in stone. The tale begins with the theropod dinosaur Sinosauropteryx and its simple tubular feathers. The story continues with Dave, the fuzzy raptor, who sported complex feathers with a central shaft and barbs with interlocking barbules. The last chapter was the development of asymmetrical aerodynamic flight feathers used by Microraptor to glide and its relatives, the birds, to fly. Without the magic of the Liaoning fossils, this revolution in thought would have never taken place.
It just seems like all the pieces are coming together right now on a question which that we really only before this had one piece of evidence for, and that was Archaeopteryx. So it's a great time to be studying these things.
The discovery that modern feathers evolved in raptor dinosaurs before the origin of birds or flight has blurred the line between the 2 groups. It challenges the imagination to see some of our most familiar dinosaurs, the meat-eating raptors, including the fearsome Tyrannosaurus rex, in this new light.
I was so struck by this that I took my kids and I sat them down on the couch and I said, "Listen to me, kids. This is really important. I want you to remember this. Tyrannosaurus rex had feathers."
By combining discoveries in the field of paleontology, developmental biology, and molecular genetics, scientists have shown that evolutionary theory can provide answers to fundamental questions about the history of life.
Because all these features that all of us have always thought, well, that's a bird, look, it has feathers and it flies and does this and that. It sits on its nest and it rolls its eggs and it sings to defend territory and attract mates and on and on and on and on and on and on. You find out almost all these things originated before the crown, that is, all the ancestor of all living birds today. All that stuff appeared long before that. Most of them in a context having nothing whatever to do with flight.
In just the past few years, scientists have come closer to solving one of the great mysteries of evolution. The feathers we once thought set birds apart now place them in very different company.
We don't have to talk about how dinosaurs went extinct anymore because they're all around us. Once you realize that, you can never look at a bird the same way again. Care to join me in a little dinosaur watching?